was significantly more acidic. Okay? You're looking at something on the order of a phenol functional group. Okay? So pretty darn acidic. If we go through and now switch it to, say, just a standard aldehyde, or even a ketone for that matter, that acidity drops off. Okay? Not that much, unfortunately, though. We're still looking at something that's relatively acidic. The acidity of this guy comes in at something about an alcohol, somewhere around the acidity of water. So if we go through and now add a strong base to this, that base is for sure going to be strong enough of a base to be able to remove some of the hydrogen. Okay? And we end up with our enolate. This is an equilibrium reaction, meaning that we do run the reverse as well. Okay? And in fact, when it comes to this type of chemistry, with this base, we see a large preference for the starting material. Okay, so if we were asked to decide between these two, what was our answer? It's our starting material. Okay? But there is a small concentration of the enolate present. Okay, so what chemistry is available to the enolate? We have a negatively charged carbon. That negatively charged carbon can act as a nucleophile or a base. Okay, if it acts as a base, we do the reverse reaction. Well, that was kind of boring. Okay, if it acts as a nucleophile, what does it need to react with? An electrophile. What charge does an electrophile carry? Do we have any atom that is remotely positive that is not hydrogen? Where? What carbon? Our carbonyl from our aldehyde. Remember, we're running this in massive concentrations, so there's tons of these molecules floating around. The likelihood that that enolate bumps into just a standard aldehyde is actually pretty high. Okay, which means what ends up happening is we get the nucleophilic attack from our enolate on our carbonyl, which kicks the electrons up onto the oxygen. Okay, the result is that we end up with this product, okay, or this, let's call it an intermediate, not a product. Is this structure stable? No. So what's it going to do? We could attempt to do resonance. What would we try and move for our resonance? Which oxygen? The one with the negative charge is a reasonable option. We try and move those electrons down. How many bonds would that carbon below it now have? 5. It has 5. There is an implied hydrogen, okay, which means there's too many bonds. What do we have to do? We'd have to break a bond. What bond would we break? Would hydrogen likely take the electrons? Why not? Why is hydrogen not going to take those electrons? It's a bad leaving group. Why is it a bad leaving group? It's not H+. It took the electrons with it. It's H-. It's tiny, and it's not electronegative. 2 big checks against it for being able to take electrons with it. Okay, so that's not going to happen. Try again. Okay, there are some carbons. Would carbon be willing to take the electrons? No. What does that mean? We only have one bond to break, and that is the bond we just made. No resonance. Try again. Yes?
Where, I don't get where they're coming together. It's attacking the carbon,
Yep.
carbon, but what exactly?
Let me try and color these things. So this one will be our red carbons. That is this guy.
Don't you have an
Oh.
acidic hydrogen on the alpha carbon?
Talk about that in a second. And then our starting material. There. You see it a little bit better now? Oh, and, oh, I just deleted all my arrows. Does that make a little more sense?
What about the hydrogen?
Which hydrogen?
In the red structure.
As in, where did it go?
As in, like, where we use that one?
I don't know what you mean.
Like.
Okay. You can ask me after class. I'm not sure what you're referencing by saying the hydrogen. Until the attack occurs, there's no more acidic hydrogens on that material. We could make the argument that we do have another acidic hydrogen now on our product. Where's that acidic hydrogen? On our alpha carbon. We do have an acidic hydrogen there as a possibility.
But they're the same.
Okay, but they're the same, so we can focus on it being one. Oh, is it more acidic or less acidic than we started? Those hydrogens, our alpha hydrogens. Probably more acidic because 2 oxygens, so we get an inductive effect. So if we have that acidic hydrogen, we could potentially have our oxygen pick up a hydrogen, and that could be our acidic hydrogen that was picked up. Or it could come from somewhere else. We don't really know. Okay? But that oxygen is very likely to pick up a hydrogen. Okay? Remember, when we started out this whole process, we said we were in equilibrium with our enolate. And we said we primarily favored our ketone. Okay, so there's a strong favoring for keeping the hydrogens on our structure. What we now have is what's referred to, and this is where the general name comes from, is an aldehyde and an alcohol, or aldol. That's the overall name given to this chemistry because it was probably first discovered with aldehydes. Why aldehydes first? More reactive. Okay, so someone probably mixed some aldehyde with base by accident and all of a sudden got this weird product coming out of it. Okay, so that's where our chemistry comes from. We don't have to use an aldehyde. We can use a ketone and we can use an ester. The primary issue, though, is we have to have that alpha hydrogen because that's what allows us to form the enolate. If we don't have those alpha hydrogens, we can't form the nucleophile. Without the nucleophile, what happens? Nothing. Okay? Very rarely do we actually end up with the aldol product. Okay? It can happen in certain circumstances, but it is fairly rare. And we addressed kind of the primary issue with that. Okay, we still have enolizable hydrogens on our structure. These could potentially continue to polymerize or add on more, do multiple aldol reactions. But it starts to become sterically hindered. So it's not going to be as good of a nucleophile. But what happens if we do decide to make that carbon negative? It is more acidic, and it is resonance stabilized with our carbonyl. But is there another positive charge floating around? Let's say that again. Is there another partially positive atom nearby? Where's that partially positive atom? The carbon from our alcohol.
And it pushes out that oxygen.
And it can force the OH to leave. It has to force it to leave. Why can it not leave on its own? It's a horrible leaving group, so it's gotta leave on its own. The net result is we've done an elimination reaction. That elimination reaction results in the formation of, eventually, H2O, which is where condensation comes from as a term for these. So our aldol condensations are because H2O overall is kicked out of the structure. When the hydrogen and the OH are removed is kind of irrelevant. Okay? We're looking at the overall scheme. So So the net result is that we have an aldol condensation all the way through this. Yes. So 1, 2, yeah, Teresa.
So because of the steric hindrance, because if you start, you've got all of these molecules working in solution, and you have your, positive charge, negative charge, partial positive, whatever.
Yep.
Do you end up with a net result being very small, if anything, of
So-
the product?
This product you do actually get in fairly high yields. The aldol does work out fairly well. There are a variety of other places that it can go, or other side reactions that can happen. And as we'll discuss after this exam, we have now a structure that is now referred to as an alpha beta unsaturated, in this case, aldehyde. Well, that alpha beta unsaturation introduces new chemistry. That carbon of our beta carbon of this alpha beta unsaturated ketone is a rather good electrophile. And in the presence of a nucleophile, we can do an addition reaction at that point. Okay? Well, we do have nucleophile floating around. Is that something we're particularly concerned about? Well, remember the balance in that first reaction. It is an equilibrium that favors primarily the ketone. What's the relative concentration of our nucleophile? Very, very small. So we aren't particularly concerned about our forming product reacting with our starting nucleophile because the concentrations are just not there to allow for that reaction to occur. So we'd have to do some other tweaks to it to force those two to interact with each other. Okay, and I saw your question, but I'll go to Sarah first.
Will we only see this Aldol reaction in the presence of the base?
It can be run under acidic conditions as well. It is primarily done under basic conditions.
When the homework done, basically they'll just give us that with the base and water, and that's it, and it will react then.
That's what we just said. All we did here was just work through all the steps. What they're expecting you to do is what you would see on pretty much any exam or any homework would be, what's the product? You were given only the aldehyde and the base. And under
Oh,
those
you're expecting
conditions,
us to know that-
you're expected to know that all of those other steps have to naturally fall out of it. Naturally. Okay? This is a big departure from what we've typically seen. If you think back to first semester or even earlier this semester, we took species A with species B, we reacted them, we ended up with a product. Now you're taking species A, doing a reaction to make species B. Now that you have species B, react it with species A again. Okay? So you have to do a lot of back and forth within each of these. If you generate something that is active, that active species you have to realize can react with starting material that has not yet reacted. It definitely makes this trickier, but that's part of what makes this section fun. Just don't like getting tested on it, but it does make it more fun. Okay? Other questions with this? Okay. Yeah, so our big summary so far is that our aldol reaction often has secondary chemistry following it. Okay? Almost always it's some kind of elimination, which means we will see a pi bond form. Where that pi bond forms is another issue. If we're starting with aldehydes, that pi bond may form in such a way that we get an alkene. If we start with a different functional group, say an ester, the pi bond that may form may be a carbonyl instead of an alkene. It all depends on the chemistry available to you at each of those steps. What we've got within this outline is the big bulk steps that you need to be concerned about and connecting those to get those general groups. Questions? Because the next one was everybody's favorite slide last week. You guys want to go through and try and do some more practice on your own again? As far as I could tell, only 2 people really got through most of it, but still had some problems with it. Do you want time, or should we just start cranking through it? Okay. If you got questions, raise your hand. The first one, big ol' ugly and nasty, but I think I went through and ended up getting it. You should notice for that first one that we don't go through and do the condensation or the elimination reaction. And that is because we do not have an acidic hydrogen. Right? For our enolation or our elimination, we would need an alpha hydrogen. So we need a position or a hydrogen that is alpha to that carbonyl. So I just drew one in there, but how many bonds does that carbon then have? 5. Okay, so I can't just pretend that there's a hydrogen there. The other option is that we could try and pull a hydrogen from over here. Okay, and do a standard elimination reaction. Not a bad idea, except if we did that elimination, what's leaving? Hydroxide, a horrible leaving group. So if we're going to run under standard elimination conditions, we need a good leaving group. The reason why we don't need a good leaving group under the previous circumstances to do our condensations is because we have a very acidic hydrogen. Right? That acidic hydrogen changes the dynamics of the elimination reaction and allows it to actually occur. So in this case, we stall at the aldol. We cannot do the condensation. If we move to the next one, we don't have any alpha hydrogens. No alpha hydrogens, no nucleophile formation. So we get nothing happening. We get no reaction. If we move to the next one in blue, we end up doing our aldol with a condensation because we do end up having enolizable hydrogens. All right, so what we would do is take a look at our initial position. There are 2 hydrogens there. As long as we got 2 hydrogens, we can do the condensation. All right? Next part of this would be, how do you draw these out? All right, a lot of people are struggling with that. I don't blame you. It's really hard to go through and draw them out. So let me draw out what I would go through and do, just in case you guys weren't watching as I drew them in. So I start with my nucleophile. Typically draw that on top. That nucleophile is going to attack another aldehyde down below. Okay, and it's going to attack at the carbonyl carbon of my other aldehyde. So there's my hydrogen. If I wanted to and stop at the aldol, I could just go through and put it there. You guys see how that kind of sort of just drop in happened? Okay. If I look at that structure, hopefully you see that there is another alpha hydrogen. That alpha hydrogen is what follows through and does the elimination. And I end up with my final condensation with the double bond in there. Okay? So if we're going to do an aldol condensation, what you can do is start with your carbon nucleophile, find whatever your electrophile is, erase the oxygen, and stack them on top of each other. There's your double bond. Okay? Which is what I did for the next one in purple. Okay, you'll notice that an interesting dilemma happened in the purple. How many of you got both of those products? How many of you got one product? What was that one product?
With the ring.
The one on the left. Why'd you not draw the one on the right? What happened to get the one on the right? The aldehyde formed formed our nucleophile and then attacked itself. Attacked another aldehyde just like it. Is that possible to occur? Absolutely. How could we adjust our reaction conditions to prevent that from happening? We want to make sure that the odds of our nucleophile encountering the benzyl or the benzaldehyde electrophile is the highest probability. So what can we do? Add a ton of the benzaldehyde. If there's now a massive excess of that, odds are that's the one that's going to act as the electrophile, which means we can prevent the formation of the other one. Okay, so that last one was a self aldol, and our other one was what's known as a crossed aldol. Why self versus crossed? One, it reacted with itself, same molecule. Crossed, reacted with a different one. Okay. What happened in the next reaction?
Either can form
Yeah, several products.
You're going to have a lot of products. Anybody know how many products you'll have? You should have 4 products. We will have A reacting with A reacting with B reacting with B, and B reacting with A. 4 possible products come out of this. Okay? 2 crossed, 2 self. That's a mess. If we only want one of those products to come out of this, we might want to change our conditions. So what's the next reaction do? Under those next conditions, we only react our, what is that, 1, 2, 3, 4, our butyraldehyde with the base. Which means, in theory, the only one that's acting as a nucleophile is the butyraldehyde. Which would mean, hopefully when we ran our reaction under those conditions, that we would get A connected to B. But what else would we run into? A connected to A. It can do that self-Aldol condensation reaction again. So we've limited some of those alternate products, but we haven't gotten rid of them entirely. So we changed how we ran the reaction. We switched up the order, and that helped to prevent some of those side reactions. Under that last condition, what else did we change?
From OET to NaH.
OET to NaH. What is sodium hydride?
It's really strong.
It is a strong base. It's pretty small, so could it act as a nucleophile?
Yeah.
It is non-nucleophilic. A couple people have been asking about this one. Why is it not nucleophilic? It's one of those weird chemicals that I've always wondered about too, and so I spent some time looking it up to figure it out. Sodium hydride is very, very tiny, okay, and very, very ionic. With those conditions, it is virtually insoluble in organic solvents, okay, which means it does not interact. We get 2 layers, a phase barrier between our sodium hydride and whatever we're trying to react. Well, for it to act as a nucleophile, what does that hydride have to do? It has to be nice and small and get into the organic substance. Well, if it's insoluble in organic substances, can it get into the organic substance to react? No. So the net result is that even though it is ridiculously small, that phase barrier prevents it from acting as a nucleophile. So sodium hydride will only act as a strong base. How strong of a base? Very, very, very strong. And when it acts as a base, what does it produce? Hydrogen gas. What does that do to the reversibility of forming the nucleophile? Destroys the reversibility. Which means when I react sodium hydride with that butyraldehyde, I convert every last molecule of butyraldehyde to the nucleophile. Well, if every single one of them is a nucleophile, can it do a self-Aldol condensation? Nope, because there's now no electrophile. So by changing the strength of the base, I can now change my reaction conditions to make sure that the only thing I get is my AB product with no other side products. So depending on how we organize our reaction, if we do steps, if we do different strength bases, we can change our product compositions and we can get different things coming out of it. So we have to be careful with what bases are provided for us so that we answer appropriately. Kind of make sense? Yes?
When we add the hydride,
Yes.
you cause the substance to become inert, right?
Yep.
And then when I add the second one,
Yep.
the hydride in the second.
Is the hydride present anymore? we have a massive amount of the nucleophile. So the reason we go in step 1 and step 2 is after step 1 we're done. Everything's been destroyed. Now we move to step 2. We take our most active thing from step 1 and we move into step 2. That's the only thing present.
After step 1, we don't have any hydride.
There's no hydride left.
Oh, just
Yep. So that's what that's why we number our steps. Okay? When we started off to begin with, there aren't any numbering. We just take an aldehyde and we take our base. We got tons of both. In step 1 in this case, we've got a ton of the butyraldehyde and a ton of the sodium hydride. Those two react with each other to form the nucleophile. Now that the nucleophile is formed, now I do step 2. Now in step 2, I just have the nucleophile and the, acetaldehyde. And we end up with our one product. Okay? So our lessons from this. We need an alpha hydrogen. So in that one case where we didn't have an alpha hydrogen, no reaction could occur. If we do a crossed aldol reaction, be it condensation or not, we have massive control issues. Okay? Way too many things can possibly happen. So we have to control and limit how those things react with each other to allow us to get through. Okay? So ideally, we'd set it up where only one species has alpha hydrogens. Under those circumstances, I can really only generate one nucleophile. I should maximize or be able to maximize my yield of my crossed aldol product. The other option is I allow only one species to enolize, okay, by using a different base control. So we've got different ways that we can control our aldol reactions by either changing the amount of reagents or by changing our bases. Okay? Those are the big lessons out of our aldol reactions. Questions? Yes?
back to the previous slide.
Where I don't have anything written anymore? Sure.
The last one, okay. And after we have the carbon nucleophile reacts with the aldehyde,
Mm-hmm.
okay, we form something, or aldol.
Yep.
After, do we have hydride again to make the condensation of the aldol?
You tell me. What does your product look like?
I have a ketone and then alcohol.
Do you have any more enolizable hydrogens?
Yes, at the alpha position.
What happens?
If someone takes that one, I would have. But do we need a hydride? No, we need a.
You just need a strong base. You actually don't even need that strong of a base present. Okay.
Which one is
Oops.
the strong base here?
Oh, there's a hydrogen there.
Which one is the strong?
You generate this species right here, gets turned into what? Miscounted my carbons. What can that negative charge act as?
Nucleophile
Or,
or base?
do you have a base?
Oh, you mean that one still in the
Yeah.
solution, so that one take the hydrogen.
That could take the hydrogen. You also have a hydrogen that is acidic enough that it could potentially self-catalyze. Okay, so we don't need to worry about a base to remove that hydrogen. Okay. Other questions? Where did the time go? Kind of crazy. Can we do it intramolecularly? Yeah, of course we can. Okay, why not? So if we take a look at this starting material, okay, as with all aldol reactions, what we're looking at is our alpha positions. So we've got a lot of alpha hydrogens that could potentially go through and generate our nucleophile. Once we have that nucleophile, it can then react with our other carbonyl and form a cyclic structure. The question that's going to come out of this is that what hydrogens go through and do this enolization? You're going to love the answer. All of them. Every last one of them goes through and enolizes. Okay? Which one leads to product? The one that generates the most stable product. So what happens if we enolize That first hydrogen versus the last hydrogen, are they different from each other? No. Since there's no difference, then let's go ahead and just erase one of them. How about the inner? No difference? Okay, so let's erase that one as well. What happens if we enolize that purple and we have an attack over here? How many carbons would be in the ring? 6. 1, 2, 3, 4, 5, 6 carbons. We'd have a 6-membered ring. Okay? Is it not possible for the other one to do the same thing?
It is, but it's
It
only 4 carbons.
absolutely is. How many atoms would be in that ring? 1, 2, 3, 4. Is a 4-carbon ring very favorable?
Yeah.
No. When do our cyclization reactions occur? When we form a favorable ring. So pick a hydrogen, run the reaction. See if it forms a 5 or 6-membered ring. If it does, cyclize. If it doesn't, try a different hydrogen. Okay? Yes, that's tedious. Okay, but the idea is to look and identify that reactivity, and as quickly as you can, like we just went through and numbered out, said, okay, what happens if this occurs? You'll notice that in my drawing, did I ever show a negative charge? No. Okay, all we're trying to do is identify where that chemistry can occur and say, okay, now it happens, let's see. Count it out. Kind of makes sense? So, as long as we form a 5 or 6-membered ring, we're good to run with those. Okay? Remember that. Anytime you've got an intramolecular reaction, or you have a structure that has 2 sites of reactivity within it, think about intramolecular, because it could potentially happen. Last reaction that we're going to end with today is the claisen reaction, which I think all I've got is what's on this slide. Yeah, it's the last slide. It's the exact same idea as the aldol reaction. The one difference is instead of using an aldehyde or a ketone for our carbonyl source, we use an ester. Okay, that's it. So given these conditions, go ahead and take a stab at it and see if you can't come up with what our product is. Actually, now that I think about it, I might have this broken. Aldol, our base comes in, removes a hydrogen. We form our active nucleophile, which can then go through and react with our starting ester. You're saying I'm drawing it less messy?
No, yeah, because you put OME instead of the oxygen and then the group
Oh.
sticking out there.
Did I lose a carbon too? I lost a carbon here, yeah. So we'd end up with this intermediate structure. The carbon right there, our purple carbon, is particularly unstable. So what ends up happening is that we have the electrons come back down. Now we have a leaving group. That leaving group gets kicked out, and we end up with this guy, which looks all sorts of weird and funky, okay, but we could probably redraw that to get it back to our proper structure. Okay? Is this the correct final answer? Did I miss a carbon? Looking at some weird faces. Thought I got all the right carbons. No, that should be right. Ish. So, those of you with funny faces, I want to ask you, what do you think is wrong with it?
It's continue on because there's another.
There is an enolizable hydrogen, but what could that hydrogen do? So we can pull that hydrogen off, and we'd end up with this negatively charged species. What would that negative do?
It's gonna form another bond. Give resonance.
So there's lots of resonance stabilization to suggest that that hydrogen is exceptionally acidic. So under most circumstances with our claisen, we usually run it as a two-step reaction as well, where we follow it up with H2O, maybe even just H+, to reprotonate that. Okay, but could that negative charge do anything on its own? It is a nucleophile. It could potentially do another reaction, but it comes down to, again, concentrations. The relative concentration of that nucleophile versus the rest of the nucleophiles in there, or the rest of the electrophiles, is so low we would not expect a lot of a second reaction happening, or a second claisen. So we would probably stall right here, follow that up with our H+, and we'd put on our hydrogen. Okay. Are you guys happy with that then as an explanation?
It doesn't do a transesterification.
That's what I was fishing for. What are you talking about?
Because you would need to provide an H+ first, right?
No.
To make that carbon more.
What do you mean by transesterification? So let me clear everything away. What do you mean by transesterification?
The oxygen attacking the carbonyl carbon, and then kicking out the
Is
methoxide.
OET a good nucleophile? Yep. What happens? We do a transesterification. I was being kind of obnoxious. Two things to watch out for. We do the claisen reaction and the transesterification. With those reaction conditions, you will see that transesterification happen.
So the carbonyl oxygen does not need a hydrogen.
It does not need. So the transesterification can be base or acid catalyzed. It does not have to be acid. You can do it base.
Can you repeat that?
Which one's predominant?
What do you mean which one's predominant?
The claisen or the trans?
Both.
esterification?
Both happen. You get this product. You get the transesterification and the claisen product. Okay. Why would we ask this on a test? To see if you're paying attention on what can possibly occur within your reactions. When we move into the ester functional group chapter after exam 3, we'll run into this a lot more often. Okay? You have to watch out for that transesterification, which means if we didn't want the transesterification to occur, what should we have done to fix our reaction? The easiest way to do this would have been use methoxide as our base. Then we wouldn't have to worry about the transesterification. Not because it's not happening, but because it doesn't change the structure. We get the same answer. Okay? So watch out for those sneaky kind of backhanded base
So you can
tricks.
get both products.
Yeah. So you'd get a mixture of all sorts of products coming out of this. Okay? And this really all centers around this intermediate, which is the same intermediate that we see with the aldol. Sapling has you go through and draws the parallels even further and says that this hydrogen is acidic and can go through the elimination once we acidify that, okay, to eliminate the OH as a leaving group. Oops, sorry, not that way. To eliminate the OMe. So what they end up going through and doing is still an elimination reaction, and what we would end up with would be this product. What's special about that product? That's an enolate that, according to resonance, goes back to the ketone. So sapling actually shows a better parallel, in my opinion, to our connections to the aldol chemistry. Okay. So I can't remember if that's part of chapter 24's homework or not. I think I included that mechanism in it. Okay. So that is it. I do see you. Give me just a second. That is it as far as the claisen reaction goes. It is in the homework. I think there's one question on the exam on claisen. Okay. You're ultimately responsible for your claisen ester reactions anyway, because you did that with the malonic ester synthesis. Okay. Same chemistry came out of those. Yes, we.
Can you repeat the claisen esterification? how you get to the other product?
The transesterification occurs because OET acts as a nucleophile.
Oh, okay. It doesn't take the alpha hydrogen.
It does both.
It does both. Oh, so it can happen at the same time.
Not mechanistically at the same time, but in the same solution,
In the
yes.
conception, we can have both products.
Yep.
Oh, okay. Thank you.
Okay, so that's it.